to the ohmic losses due to the resistance of individual cell components and to the diffusion and in the bulk of the solution. That's what very similar to the traditional concentration polarization phenomena that we've been discussing. So these kind of phenomena are present. Sometimes they can be present, all of them, they can overlap, so we can have significant deviance. That's why when you are just making your fuel cell study, not only the membranes are just assembling, the system is to be done, but we have to work and to make progress in the control of the diffusion in the system, and that means in distribution of the reactant that we are supplying, for example, in trying to avoid all this resistance, all the ohmic resistance, and in the study of the cathodic and anodic compartment. Some of you having experience in fuel cell on the 10th floor, we have been working with MIA how to prepare this catalyst distribution in some matrix in carbon normally, and just pressing it, just forming these components of the fuel cell. So that's something that we have to remember. One more problem that we have, which is related basically to the concentration polarization phenomena, is the fact that in the fuel cell we always have a limiting current that we have to consider. That is the same kind of limiting current that we have in electrodialysis process, just the same story, and the origin is just related to the property of the membranes in this case, as in the traditional membrane operation, because some of the ions, and particularly in fuel cell, the protons, which are the one that just transfer the current from one side to the other side of your membranes, they can have a much difference in the velocity that they have moving in the compartment, in the solution, and in the membranes. Particularly in the membranes, we have to remember that the transport number, that means the amount of current transported by one ion, in this specific case would be proton, is basically covering 100% of the current going across, if the membrane is perp selective, as we are looking in this case. Normally in the solution, the amount of current is related to the transfer of ions, positive and negative. And in first approximation, the transport number for cation, anionic compounds and the cationic is very similar. For most part of the salts, you will find 4951 or 4852, but basically they are not too different. The mobility of the ions in solution is not too different between anionic compound and cationic. Very different is what happens in the membranes, because only one ion is going through, which means that what can happen that if these ions don't arrive to the interface, or when they arrive at the interface, they quickly go through the membranes, and the diffusion cannot be sufficient to keep constant the concentration, just because 100% of the current is transferred by these ions across. So you have a depletion and a decreasing of the concentration of the interface, which means an increasing of the resistance, because in this solution current is transported by the ions. If there are no ions, no current. So you have a limiting effect here. That is the situation that we have at the origin of this kind of phenomena. So it basically is concentration polarization, the membrane surface in the compartment where the solution is present. And if you make our mass balance, the situation is that the total flux of the counter ion through the ion exchange membranes, remember we defined what is counter ion, which is co-ions. Counter ion is the ion that have a charge which is different from the one of the fixed ion in your membranes. And this, the flux here for this species, in our case, will be basically this I will be H plus, because that's what the situation. If you are in a battery, in a lithium battery, will be lithium ions. is given by the diffusion, the diffusive flux, and migration flux in the boundary layer, so the sum of these two. So the total flux can be defined by this transport number, which is nothing more than, is defined by the transport number, that means telling you how much of the total current is related to these ions, which is defined as the ratio between this current that is going through and divided by the charge of the ions and the transfer and the Faraday constant. If this, what it can happen in the situation we have been describing. So the transport of the counter ions through the boundary layer will be given by this kind of expression, where we have that the diffusive and the migration are given by the relationship gradient in the concentration multiplied for diffusivity plus the amount of current related to the ions that we are considering. And we can put together this equation and the definition of transport number, and we will have the overall current that is present in our system given by this kind of relationship. Faraday multiplied for the diffusivity on the charge of the ions multiplied for the difference between transport number in the membrane phase and in the solution. And in the specific case we are considering this difference here, this term will be approaching 0, basically. There is no ions across. Tm will be about 1, and for the gradient of the concentration across. That is just the general expression. If we just integrate, now if you just substitute to the diffusion coefficient the term that we know, and the single ions, and we integrate in the, also in this case we can use the theory of the film that we have been using describing all the concentration polarization phenomena in our membranes. That means we are assuming a boundary, laminar boundary layer at the interface membrane solution with a certain thickness that where everything is linear instead, and right in the appropriate boundary condition you can integrate, and so the overall current will be given by this kind of expression. Basically is given by this product for the diffusivity for the Faraday, that this is the difference in the transport number for the driving force of the system, with nothing more the difference of the concentration of these different ions on one side and on the other side of your membrane. These are Tm and T are the transport number in the membrane in the solution. Ds is diffusion coefficient in the solution. The CSMD and the CSBD are the salt concentration at the membrane surface and in the wall. That means when everything is well mixed and the solution is homogeneous, is concentration, no concentration gradient. And theta is the thickness and the charge of the single ions, and the stoichiometric coefficient if there is any problem of in the separation of the stoichiometric coefficient will be present, and the cation and anion are just the two components. What is this limiting current we are describing? The limiting current will arrive when the concentration of the membrane solution is approaching, its limit is going to 0. It's going to 0 because the transport number in the solution is about 50%, 0.5. Transport number in the membrane is about 1. So it can happen that the ions arriving will go through and there is not sufficient ions approaching if you don't help the situation. If through some flow dynamics you can steer, for example, and that means a way to make the system, when the concentration profile starts, you can try to help the not only diffusion, but appropriate flow dynamic condition can help to have to minimize the concentration profile, exactly as we have been discussing in reverse osmosis or any other problem. So for the concentration at the membrane interface approaching 0, we define the limit current, which is nothing more than the product of this diffusion coefficient for the Faraday divided for the transport numbers difference multiplied for this CD on the zeta, assuming that this term, this C0, the CS is going to be 0 at the interface. So that is the definition of current density. What does it mean? That if we are approaching this kind of current, as I was mentioning, if there are no more ions at the interface, the resistance, the ohmic resistance of the system is going up, and that's what you measure when you're doing your experiments. If you just measure the current density as a function of voltage drop in your system, what is happening at one point, initially you are just increasing the driving force, your voltage, you just increase this system does not work. Anyway, you are increasing the current density, but at one point, the resistance is linearly, as expected from this equation, but arriving at a certain value, the limit current, the expression we saw before, the current density is going, the resistance is increasing drastically, and you have totally different behavior in this system. So that is the point that you have to consider this kind of phenomena, and what you have to do is basically solve the problem of the difference between the transport number in the system, such a way that the difference in the concentration will not be too significant between the bulk, the core of the solution, and the interface. In principle, you can help the situation playing with the temperature. You know that all the transport parameters, the diffusion coefficients, viscosity, etc., are functional of temperature. So if you want to increase, for example, diffusivity, that means faster ions moving the solution to the surface of the membrane, you can increase temperature. And with increasing temperature, viscosity is decreasing. That means also is a way to help this, to avoid too much another resistance that you can have in the system. That, in fact, people have been working in this fuel cell at different temperature, and you have for them 80 degree, 100 degree, 200 degree, and the maximum efficiency in general is higher at a lower temperature in principle. But just the situation, by the way, there is a mistake here. This is not, oh, okay, no, it's H2. I thought it was H2 all the way. The maximum efficiency suggests that you can have a better performance at a lower temperature, in principle. But vice versa, what people are doing are working trying to work at higher temperature, because the theoretical efficiency is higher at lower. But if you want to control the flow dynamic phenomena, it's better to increase the temperature, because increasing temperature, you have just better control of the diffusion and lower viscosity, etc. So that's the situation that is the real situation that we have. And normally, the membrane that you have to apply in this kind of system are membrane that must have good property also at high temperature. And that is one of the competition we have between Nafion and other membranes. Nafion, as you know probably, is quite interesting, but at high temperature, overcoming 120 degrees does not work. It's losing most part of the properties. And other polymers, if you can operate in the same around the same temperature, you can have these benefits here, and which can overcome some of the problem compared to Nafion. Well, that is a typical plot. Some of you were making these experiments, and this is the kind of what we call polarization curve that are giving you this different deviation from the behavior that is expected. But this kind of decay here is just evidence of the polarization phenomenon. Remember that these polarization are complicated systems, are not easy to handle, and have nothing to do in principle with the chemistry of the membranes. And they can completely kill your system and just go to very low voltage if you don't know how to well control this. So not only good membranes, but good design of your system, has to be done. Now here we can look a little bit just in detail what is happening in our fuel cell when it's working. As you can see here, what we have been discussing before, that is just a situation in which we have our two electrodes in the compartment, and hydrogen on the anode is arriving, and the catalysts that are present on the surface just help to split these hydrogen molecules in H+ molecules. You have oxidation at the anode, and so you are producing the electrons. On the other side, what we have is oxygen, and oxygen is just air normally, because you just put the 20% of air is oxygen, and this is cathode, and the catalysts that are present also here, they just use the possibility to have the reaction between the H+ and oxygen for forming just water. So what you have, if these electrons that are produced here and will go through an external metal, your copper or a lamp, you just produce electricity. You produce light because the electron is just our electricity is going through, you will switch on your light. And that is the schematic system. Looks easy, but it's not so easy. The reaction you have to consider normally are this one, hydrogen becoming H+ and producing, being this as two molecules, two atoms of hydrogen are producing two protons and two electrons. That is at the anode. At the cathode, oxygen reacting with hydrogen, capturing the two electrons produced at the anode and forming water molecules. So the overall reaction is the one I was mentioning. Eventually, if you're studying the other case of interest is the methanol, what is called methanol direct fuel cell. The reaction is this one in this case. At the anode, you have the same. You have your methanol interacting with water, producing CO2, hydrogen, and the electrons. And these electrons will react with oxygen, forming water. So this reaction is different, but basically the same mechanism. The overall reaction is this one, methanol plus 3 of 2 oxygen, CO2, and 2 molecules of water. In both cases, what is interesting, both methanol, both just hydrogen, you just produce water as a product, and that is environmentally quite interesting because it's useful and is not giving any contamination. That's a little bit more than this. You can see here the oxygen is just supplied to the cathodic compartment. Eventually you can have a compressor, something that is pushing the oxygen in because the oxygen has to move around. On the other side you will have your cathode, anode, where this hydrogen is arriving. That can be in case of methanol. So you have a liquid phase. You can just circulate methanol continuously on one side, and you just compress air on the other side. And here you have at the end, you just have CO2. That is not the best that you can produce, as you know, but you can produce CO2, and you just have your, again, exactly as here, the electrons that are present, they will circulate in external area, and they will produce electricity and eventually light. As you can see here, there is a difference in these two systems because here methanol is a liquid phase. And so you have to, the geometry of the cell is different. In both cases, you can see the system, you have to recirculate, you have to control the flow dynamic of the system on both cathode and anode for minimizing, trying to minimize at the best the different over potential that we have been discussing before. And here, that is, you cannot work here in a static system. If there's no pump in here or pump there, the system has very different performance. The over potential are becoming the negative controlling step. So in both cases, you can see here you have things moving. That means when you prepare your compartments, and you have to study carefully thickness, geometry, spacers for making it the best without consuming too much energy here, but well-controlled interfacial phenomena and the distribution also in the solution. Again, a little bit more in detail, which kind of catalyst normally people are using. So you can see here that the hydrogen, that is a fuel in our system, is just supplied to the anode through this plate, well-studied plate, in such a way that the distribution on the catalyst is much more efficient than possible, minimizing this activation phenomena, this over-potential that you can have there. So there's, I know on one side before, and oxygen on the other side is channeled to the cathode of the cell. Also here we will see there is a well-designed way of doing this with some spacers, some channels, such a way that you have homogeneous distribution. At the anode, normally there is a platinum catalyst. That is the one that split the hydrogen, making having the oxidation to H+ and electrons. On the other side, the polymer electrolyte is just the one that we have been describing. We will describe soon again as permeable only to positively charged ions, such as only this proton can go across, and we will create in this case our current. At the cathode, the electron and positively charged ions recombine and they flow out. So that is the schematic. Now if you are working on this, you will see the system is a little bit more complicated than expected. It's not just a membrane, etc. You can see here for a single stack, keep in mind that any fuel cell is normally a set of this one. These normally are 10, 20, hundreds. The overall potential voltage you can obtain in the system is related to the one of the single cell multiplied for the number of the cell. And that is the system that people are working on. And you can see here again, you have these repeat units, but you have the bipolar plate and these final place in the system just to have an appropriate system where the gas flow channels permit homogeneous distribution and avoiding the kind of phenomena we are talking before. Single cell, well done, normally give you a voltage of the order of 0.607, and what you are doing normally you just combine in series all of them, and the total power, the watts that you can obtain from this cell is nothing more than the voltage for the current, but each one of this voltage and this current will be the one that you obtain by multiplying the single one, the 0.607, for the number of the stack that you, for the number of the cell that you put in a single stack. So that will be just the total efficient, total result that we can have in the system. I was mentioning before, and some of you probably have been doing some experience on this, that the way of doing is this system has to be as much as possible very small. So when we are talking about catalyst, cathode, anode, at the end the system is just one membranes, and on the surface of the membranes, on one side and on the other, you just press and you make a coatings basically of your catalyst on the acting just you increasing a little bit the thickness of the membranes, but you don't have another compartment as was done initially, and as is done eventually in the big fuel cell for stationary system. In the small one, the one that you have in your you will have in your car or in some of your instrument, you can see here we have just this plate, gasket, gas diffusion layer, catalyst, and membrane. And these things are very well combined. This MeEA is nothing more than palladium for the anodic and cathodic reaction, and this palladium for the anodic. For the cathodic, you have this palladium mixed normally with ruthenium, but it can be some other kind of system. And the way of doing that, you support everything on some carbon black, having at the end about 300 nanometers. And there is a machine on the 10th floor, if you want to see, just for forming this film, this layer, and pressing in such a way that that's becoming very, very thin layer on your membranes. And that's, so you can combine tens or hundreds of these single units in a relatively small volume. That is the MIA that you are preparing. So at the end, that's what you have. You have an anode electrode, platinum support on carbon with polymer matrix, and the cathode, something similar, where you have platinum event with the ruthenium, etc. And carbon black is one of the most traditional. There are companies that became famous and are controlling the overall market. Some companies are producing the naphthalene, and they control the fuel cell market by the production of these membranes. Other company, this is a big, well-known company, this Italian origin, De Nora, just produced the electrodes. Because making the electrodes is not easy at all. And as we have been understanding, controlling the behavior of the electrodes can be important as controlling the properties of your membranes. Because if you have an ideal membranes with transport number 1, etc., and you are not able to control the overpotential, and that means the behavior of your catalyst at the interface, etc., you can block the performance of the fuel cell exactly if you don't have a decent membrane selective only for protons. So all these different components has to be very well studied and very well understood. And there are experts in making membranes, experts in making the electrode, basically. The polymer we are using, as we have been already discussing, for making our membranes, has to be polyelectrolytes. Polyelectrolytes are this one, we already discussed, I think, a little bit, in which we have fixed ions, charge with positive or negative, fix part of the structure of your polymer, and some counter ions having charge opposite to the one of the fix that we call that are just mobile, and that they neutralize the fixed charge. So the overall system is neutral. The number of counter ions has to be in principle equal to the number of co-ions. But what is happening here that if one co-ions is diffusing, because you are applying, for example, different voltage between the different the electrodes, when trying to penetrate, the co-ions having the same sign of the fixed ions cannot penetrate, because as soon as you penetrate, you violate electroneutrality. So there is a big pushing of these ions out. The counter ions are easy to move, they're mobile, and if you push one of these ions out, applying a driving force, one of the ions present will move out. So there's no problem with counter ions. So the counter ions are free to move, and they can move, but only the counter ions. The co-ions in this system, they cannot penetrate, because if they not penetrate, there is nothing going out, and you violate electroneutrality, which cannot be violated. So we have fixed groups. The origin normally of this fixed group can be sulfonic group. That's typical. Most part of the polymer we are using, the origin of the proton are coming from the dissociation of this SO3 H+, and that's what is happening, that at the end you have SO3- as cations. And it can be also phosphoric groups, or in some cases weak acid. This strong acid is sulfuric acid, basically, and normally, but you will find the membranes. Japanese are doing membranes with some weak acid. So instead of using this sulfonic, use the carboxylic group, and that is the COO- as cations. But this is a weak acid, so the level of dissociation is lower, so the charge density can also be lower. But that's normally what we are talking about. And we already described, when we were talking about the nanofiltration, how the system really works in terms of Donnan exclusion. Dominant exclusion is kind of phenomena that is controlling the mechanism of transfer in these ions. As it's telling, depending from the charge density of the polymer, you know at which concentration you can have a transport number approaching 1, or transport number is not a constant. Transport number can change in different situations, but you have to try to have the highest transport number possible in your system. What we want to have in our membrane for fuel cell, very high proton conductivity, only proton, no electronic conductivity, is a leakage, you tend to avoid any electronic conductivity. And also we want to have, again, to avoid any leakage and any decrease in the efficiency, as much as possible, low gas permeability, hydrogen and oxygen. We don't want to have the gas mixing without having the reaction at the interface and producing proton and reacting for making water. If they just diffuse, is a leakage for this kind of application. And also for methanol, if we are using direct contact, if the methanol is going across, this is a negative fact. This is one of the weak aspects of Nafion. Nafion is permeable to methanol. So people working on looking for new membranes, they are looking for membrane that, for example, can work at a higher temperature, where Nafion has some limits, or looking to membranes where polymers, where the methanol transfer is very low compared to the one that Nafion has, and the same for the gases. These are systems which have oxidation reaction, so the environment is quite severe. That means chemical, thermal stability is requested. Mechanical stability also, you have to make a lot of these membranes in big size if you want to increase, and eventually not too high cost as normally happen today. And the situation is, today there is Nafion is a dominant. There is not real competitors to Nafion, except some special case or something very similar. In Japan, they are producing some other Flamion and Permion. There are some other polymers similar, but not Nafion. However, Nafion is still dominant, and that's why people are trying to do. Using fluorinated polymers, also today using non-fluorinated. The origin of fluorinated is basically not because we need fluorine, but are fluorinated because the chemical stability, the transport numbers for different species, etc., are quite interesting. If you can do the same with a non-fluorinated, that means a cheaper polymer normally, that can be a success. Today there are people, also in this department, but in different places, including our place, in which people are working on non-fluorinated. For example, polyether ether ketone, we will discuss here, is a typical polymer where you can have interesting performance. You make sulfonation of these polymers. So the one that you have to use, if you are using a peak polyether ether ketone, you have to make first sulfonation. Sulfonation is giving the proton that can go across, and that can be, if competing, if you can increase the charge, the density, the charge density in such a way that you can compete with Nafion, you are lucky. It's not yet happening. And I will see what you can try to solve the problem, because this is a big problem. I told you that the prediction that you have today, that in 2050, that means 40 years from now, which means tomorrow afternoon, there will be no more system electricity or energy produced by burning, combustion engine, etc., but everything will be based on the fuel cell. So there's a lot of interest to, if we don't have the fuel cell, our prediction would be wrong, because you have to do something. Anyway, fluorinated polymers are the most interesting one. For example, just the PTFE, the polytetrafluoroethylene, is a typical example. And you have with the fluorocarbon side chain, a ionic cluster with sulfonic acid ion attached to some side chains. These are the system. They are strong, very stable, for oxidation environment, reduction environment. The performance also interesting. These are not just for making publication. These are systems that have to work 60,000 hours is the minimum time necessary that we accept for becoming competitive. So we can, when we make our experiment, we are used to make for half an hour, 3 hours, etc. be happy, but you have to schedule immediately something more serious, because this is the minimum that you have to expect. 60,000 hours working. Really, the minimum is the 5,000 hours. 60,000 is a good number for real operation. But if you are lower than 5,000 hours, I think is the standard test that people have to overcome if you want to present something that is interesting. You have proton conductivity in presence of water, is the one that characterizes this kind of polymers, which is this number, 0.2 Siemens per centimeter, is an interesting number at temperature in which you can operate. Cell resistance has a certain number. These are some of the performance of this kind of materials, and they are basically interesting. These systems now are competing. That is a typical example of what is happening today. Nafion basically is this polymer here, which is, as you can see, is a fluorinated, is a perfluoro ionomers, is called, and the side chain are long, very long. This is the side chain of your system where the sulfonic group is present. So they are very important one, because they're the one where this proton conductivity, the transport number equal 1 is coming from. One competing polymer, which to Nafion today, is Iflon. Iflon, you can see, has the same basic structure, but the side chain is much, much smaller than the other one. And that is introducing some people, that some other company. This basically is DuPont. This DuPont material, this is basically Solvay material. So these kind of polymers are competing, and today there are people trying to develop membranes for fuel cell in alternative to Nafion based on this Iflon. We are using Iflon for other applications because it's interesting. The trouble is also this one is expensive. So this basic difference is for the much higher crystallinity when you compare for this short chain to the long chain, and it's the same with the glass transition for this short chain ionomer. We have to say, however, that these one are still no more academic, because they are in the hands and the patents and people trying to produce, but Nafion is still dominant. So if you want to do something better, we have to learn. We have to learn first how Nafion is working, why he has such a good performance. In such a way, you can try to overcome eventually the limits. The advantages of Nafion here: very high proton conductivity. He has a special structure, you will see, and excellent chemical, mechanical, thermal stability. The negative aspects are the one we have been mentioning already. You can have some water and methanol crossover eventually. You can have high cost. Still, Nafion at the moment costs $600 per square meters. However, learn that this means not too much. This is expensive, but you will realize, because it's dominant and there's no competition. The day that somebody is coming with a better polymer that will just overcome or compete with Nafion, what will happen? You will learn that this cost will drop down, because the money that they made already, they can have this price just because they are the only one. But if there is a second one, a third one, what will do, unfortunately, is that they can decrease the price significantly and still be competitive, because they made such a lot of money before. So that is another problem. When you want to penetrate a market, it's not just the competition is not easy, because the competitors, this price is only today, will not be tomorrow when we have an alternative. This price can become easily 200, 300. So you don't have to refer to this cost. You have to refer to the real intrinsic cost that they can eventually use for fighting with you if you want to try to penetrate their own market. Life is complicated sometimes. But the other limits that Nafion can have, as we mentioned already, there is a decreasing of the excellent proton conductivity when you overcome 80 degrees. And that is a problem, that increasing temperature, you are decreasing the amount of water that is present in the structure, and the high level of proton conductivity of Nafion is very much related to the water present in the structure. And that is one of the limits that other polymers cannot have. You see here that that is a kind of typical structure of Nafion in which you can identify three different phases. One is the perfluorinated hydrocarbon backbone, that's the structure. The other one is the side chains. We see sulfonic groups that can be ionized and giving the H+, and the water or water methanol swell hydrophilic channels. There's a lot of these, let's say, free volume channels between these different, the long chain that they are present in the system, and that is giving benefits in terms of protoconductivity when water is present. If the water is present or is less present, increasing temperature, that is a negative aspect, and so you are just losing some of the properties, and eventually if you find some alternative, that can be the way of doing. This is one of the case. This is the Nafion with the high proton conductivity, and which is positive, but for example this higher methanol crossover, look to all these cavities which are present where easily as water is going through, the methanol can go through easily. One of the possibility, if you want to do something alternative, that has been done, also some people also in this department have been studying this, and we have been working we are working at ITM on this, is to use some other polymer. This is non-fluorinated polymer. This polyethyl ketone I was mentioning, PEEK, and as you can see here, that if you make sulfonation, this PEEK normally has no sulfonic group. If you make the sulfonation is at the origin of the production of H+, and so you just have a proton conductivity, and you can have a high level sulfonation to the point that you can compete with the one of Nafion. That's being successful. Plus, what you have is that narrow channels and give you this the possibility to avoid this methanol crossover. That is the characteristic for methanol fuel cell. This can be of interest, and that is at the origin of this possible competition. There is significant, the pK, that means the association of the sulfonic group is here is about 6, and this is about 1. Also, there's a significant difference. If you just see numbers that you can check in the lab, and this is just with people present in literature, you can see here that this the difference between the system in Nafion or in this is polyethyl ketone is quite significant, but this is not function of temperature, but you can see here that if you can decrease the percolation, you can have increasing still the difference between the two cases. That is just telling you that Nafion is still better than any other polymer at the moment in this range. Here is what is reported is the permeability function of temperature. That's in both cases, both polymer is the same kind of phenomenon. It's an activated process, and so you can have this typical behavior of the two. Nafion is always much more interesting than the other material in the system. The ideal, what people are trying to obtain, is eventually, and maybe something will happen one day, to have a system where this function of this, the conductivity of your membranes as function of relative humidity has to be high also at relative low humidity. And that will be this 120, this kind of situation that you have up here. That is, today we are in this green area, working, competing around 80 degrees centigrade basically. But in this case, relative humidity has to be high. And if you can, the best should be to can operate in this, not in the yellow or in the other area, intermediate temperature, lower and low thermal, low relative humidity. And that can be one suggestion for competing with naphthalene. We were mentioning already there are other kind of materials. Some of you probably is involved in studying, so don't be pessimistic. There's still a lot of work to be done. And there are polymers which are partially fluorinated membranes. These are fluorocarbon based with some aromatic chain grafted on the backbone that can be modified in different way. So you can introduce sulfonic group, you can do carboxylic groups, because in some case also this carboxylic group can be competitive. And the physical properties are normally interesting and similar, at least to the one of the naphthalene. You can have less stability eventually, but this is minor problem because that can be improved. The performance are, however, not competing at the moment with one of naphthalene. Less durable, low performance, and less, not really competing with the other fluorinated polymer that we have been discussing before. That's a typical case, and where you can have grafting. This is this polyfluoroethylene cohexafluoropropylene main sulfonated chain. So there is a different of this polymer where people have working and spending just trying to solve the problem of having only one membranes available. So that's the origin of the main problem. Let's see if now this machine is working. Not yet. It's more than 20 minutes. Still not working. And this is the now there is also, I was mentioning some case in which are non-fluorinated hydrocarbons membrane, and that is the case of this polybutadiene styrene block copolymer. But again, there are some good mechanical but poor chemical and thermal stability, not very high proton conductivity, and this lifetime is not quite interesting as the one of other polymer. You can try to incorporate some, to improve the properties by the incorporation of some polar groups. This is one of the approach that you can follow. For example, you will see that we are producing some membrane, just you want to improve the proton conductivity basically. You can try to have some superacid and prepare what are called mixed matrix polymers, also in the case of fuel cell. Not only for the catalyst we discuss when talking about membrane reactors, but fuel cell can be the same. And so that is the different kind of performance. This is kind of phosphoric acid dope, polybenzymetazole. Polybenzymetazole, you know, is a very stable polymer, and that's why you can try to use it for different kind of application. And here there are some other one again. This sulfonated polyphenylene oxide, PPO, and sulfonated polaryl ether sulfone. So just to give you, there is many that if there is any possibility to compete with NAF, etc., people have been looking, spending a lot of time. However, all this one at the moment, there is no one that can stop you from working. Now this is the case of, again, of the polyether ether ketone. Polyether ether ketone we have been mentioning more than one time because, for example, we have been working this polymer. This is Chinese polymers, and that is a typical polyether ether ketone with cardo group, with WC. It means that the normal polyether ether ketone is not soluble in any solvent. So you cannot make membrane by phase inversion. So that people were not able to use it for a long time. Chinese, a few years ago, one of our Chinese students, in fact, has been working in Changchun, not too far from here in Manchuria, and he was able to introduce this cation group, this cardo group, in the structure of polyether ether ketone, making this kind of a peak soluble. So now when you have a peak with cardo group, you can directly, without sulfonation, in principle, cast using phase inversion, producing your membranes. And in fact, we have been producing membranes for many applications, from gas separation to fuel cell and other kind of stuff. In this case, however, if you want to use for fuel cell, still you have to make sulfonation. but not sulfonation for making it soluble. Because when you are working with just peak, you have to sulfonate to produce the membrane. So otherwise there is no way to make phase inversion. So you make sulfonation for two motivations. One for increasing, giving some proton conductivity. The other one for making the polymer soluble. When you are using this peak here, the first motivation does not exist. This is already soluble, and you can change sulfonation only for increasing or the proton conductivity. This is something that can be done, has been done. Is a promising non-fluorinated membrane material for application, and the motivation for spending time and money is that he has very low permeability to methanol, to oxygen, to hydrogen, so some of the problem of Nafion can be in part overcome, and moreover, however, does not have the same level of proton conductivity. What we have been trying to do, with some success, not yet competitive for sure, you can try to increase, not necessarily with Nafion at all, you can try to increase this proton conductivity by making some hybrid matrix membranes based on this peak, combined with some heteropolyacid, significant materials with very high superacid, basically. This is typical case one. As you can see here, if you remember when we were talking about membrane reactors, the structure of these things is similar to some of the polyoxymetallate. So the same kind of material can be utilized in for different motivation. So you can disperse on nanometric scale in the structure and try to see if something can be done for having some competition. And you can see here with different level of this kind of superacid there. Some performance are interesting, but not yet to cancel the Nafion. This is just a typical case study. So we have started from this. The one I was mentioning before is called Vitrex. That's the one that people are using for fuel cells today by sulfonation. So you can sulfonate this and after go ahead. There are some big projects in Europe based on this. The one we are suggesting is this one, in which you have this cardo group giving solubility, and after you can make sulfonation for giving proton conductivity. So this one is very soluble in many organic solvents. That's totally insoluble, basically. And so the two have this kind of different. There is a procedure with some to make the sulfonation on this one, and this is something that can be of some interest. And there's also this interesting stability. This is some structure, and there's some solvent and non-solvent you can use for your phase inversion. There's typical NIPS. You can operate at low temperature, and you can make hollow fibers. You can make flat sheet membranes, dense, asymmetric. So it's a polymer that you can handle as any typical polymer. What is here is interesting with different level of sulfonation. You can have just different performance. What's important, there is no problem of the overall structure. The material is quite stable when you make your infrared, etc. Basically no evidence of any degradation, basically, of your material. The way of doing, you are familiar, is just phase inversion, and you can try to operate. What is important now, using phase inversion that you probably learn, we will try next week to recall some of the aspects of phase inversion, because the real point that is the system giving you a lot of flexibility in tunneling the final properties. You can change the thickness, you can change the overall porosity, etc. If you have to prepare membranes with this traditional peak, you can also do it by melting, by extrusion, etc. But no way that you can really control thickness of asymmetric behavior, level of porosity. Very, very rigid system. The machine, the extruder cannot do. You can change some temperature, the viscosity is quite significant in any case, so there is no flexibility in the preparation. By phase inversion, we can do basically, I think as you learn, a lot of different things, and that's why it's interesting to use this peak where this kind of methodology can be easily applied. The mechanism is typical phase inversion, evaporation, and you have your dense film at the end, and you can have both traditional NIPs, VIPs, etc. Also for doing the composite membrane, to entrap the heteropolyacid, you can just have your recipe at the end, your protocol. For example, in our case, we just working roughly around 20% of your catalyst, of your superacid, and so you can try to increase with this kind of material the proton conductivity. Cross-section show you very nice what is important. We learn with talking about the catalyst, homogeneous distribution. Not you cannot create cluster or aggregate because that will destroy mechanical properties. It will destroy also the efficiency of this proton conductivity. That's a typical interesting distribution of this material in your structure. You can see it can be very well controlled with no degradation or no negative effect. Basically, that is what to try to show. In some other case, the situation can be different. If you want to try to do the same with other material, for example, with Nafion, and much more difficult, at least for us. You see here, you have what we were already discussing, we don't like to have. It's a big agglomerate with very heterogeneous distribution, etc. That is killing the performance, basically. With peak, we can try to do the dispersion is much better than the one that you can have, for example, for Nafion. So from this point of view, you can just try to, is a positive aspect. That's why we have been spending time and publishing. More than this, you can have again when there is no evidence of any degradation, basically, and that is important. And what is important, the most important here, because there is a weak aspect of Nafion, and we have been mentioned already, that the methanol permeability is relatively high. So you can measure this permeability to methanol and also eventually oxygen and hydrogen. This is typical permeation cell that I think you have also in the lab, in which this kind of experiment can be done easily, and you can find in the literature. And if you look to the results, you will see here that in any case, Nafion is this last one here, is much higher, the Nafion permeation, than the one of the different other membranes with this kind of peak charged with this different kind of superacid. So this is, in this case, lower value means better value than the one. So Nafion is a very high value, but forget, because that's just what make some weak aspect. And that is for basically for all the different charge density, 0.1, 0.3, 0.6, nothing changed. We have only the same kind of result. So if you want to make a methanol fuel cell, that is one of the things that can be done. You can do the same kind of experiments, not for methanol, but for the gases. Again, you can use a typical gas permeation experiment in dry phase. And by the way, just to remember that when you do typical gas permeability experiment and using this typical plot of the permeation as function of time, and that is the behavior that you can observe from this kind of plots, if you are able to do it, is you can obtain directly the permeability and the time lag. So that is the kind of result that you obtain. You can see from oxygen and hydrogen permeation, and you can calculate basically, this is the permeability is nothing more than solubility for diffusivity, and you can just try to obtain this from the time lag. That is the equation that is giving you this. You measure here on the axis the theta, and from the theta you can obtain the diffusivity, basically. That's typical experiment. Time lag determined from the first pressure increase curve. And you can obtain the overall permeability, and if you just measure the one or the other parameter, diffusivity, you can have also dissolubility, and vice versa. So that you can also measure independently, but this is the easiest way of doing. And if you do this, you can have all the data, and you can compare this Nafion performance with the other polymers, and basically you have the result that we have been discussing before. Now, this overall problem now, if you want just to study carefully the property of membranes, try to compare the final performance and to see which one is the best, one thing we have been learning in the years that is necessary to standardize very carefully the kind of methodology and the protocol you are going to use if you want really to make a comparison that makes sense and that can be of some value. So in some project that we have been carrying on in Europe, we had just the role to define how to make this comparison. This is typical big European project in which different countries are working together. In some country, people are preparing membranes. In some other country, people are testing the membranes. Some other country, in some other lab, people are testing some other performance, etc. At the end, all this data has to be put together. And the fact that there are people coming from country with different language, can be Spain, can be Romania, can be Bulgaria, Germany, Twente, etc. It's a little bit more complicated than expected. First of all, we have to try to define correctly, for example, this, the efficiency related to the crossover. For doing this, you have to identify all the different fluxes that you can have in your system. You see here that we have a list of hydrogen current that can take place in your system, the flux that where you are feeding the system, and after there is the retention stream, the permeate stream, the hydrogen crossover, the hydrogen giving just the electricity, the one having the conversion, the crossover at the cathode, this one, and the crossover at the anode. So all these things, and the purge gas. So there is 7 different fluxes that you have to consider. The one that you have really to take care is the F4 and F2, which are the most, the F4 and F2, that means the permeate stream and the hydrogen becoming electricity. But if you don't know exactly what is happening, you have to take care that there are other ones that can just change the value that you are measuring. So first thing was to be clear what we are measuring and how we are measuring. Second is to see also the different performance and how to just to check performance electrodes and the membrane themselves. Okay, the system is basically all the same kind of system, and you can see, and you have the different kind of membrane. Typical, we were working with our PEAK, and the Nafion was the one using. You can also see, and you are expert here, there's some Nafion, this traditional one that you can also try to modify. You can make some annealing, some thermal treatment, and you can also have some cross-linking or mixed matrix, so there's different kind of system. Now the most important is the protocol that you have to follow in making your experiment. And this protocol has to be very well understood from everybody making in any other lab the experiment. Otherwise, everybody is assuming that he's doing it in a certain way, you are doing it in another way, but the results are the same. Not at all. You can have a lot of phenomena, if you remember the 7 different fluxes, etc., who can change completely the scenario. So what we were doing, we established a protocol at each temperature, different temperature. In each temperature, you have a different level of composition, different gases with a certain relative humidity, 50%, 75%, 100%, etc., etc., just to try to minimize possible difference between the same data that you obtain in one kind of membranes in one country and the one in other kind of membranes in another country. And that seems to be minor problem, is not minor at all, because if you don't follow this, just because the system is much more complicated than expected, the efficiency we are measuring only F2, F4, but there are 7 fluxes that can have some effect. And these other fluxes can have different behavior depending from the relative humidity, from the way in which you are measuring. For example, the history of the experiment. If you measure first at low humidity and later at high humidity, and the other one are starting from high and going to low, you can have different results, because some effect, there are some hysteresis, and some story still exists. Normally you don't wait for months or years to reestablish the same condition, so the methodology, the protocol that you follow, going up or going down, can give you different results, etc. So that's typical case in which this kind of analysis was done, and that was just, and if you do this, you can see basically some of the result here, that the permanence of all the three gases, those just are decreasing with the relative humidity at all the temperature investigated. And now, if you do exactly in the same way, following the same procedure, the probability of making mistakes or discrepancy between the result that you obtain today and the result you obtain in 3 months from now is much lower, much higher the probability that the results are okay. Here is the effect of this, again, different level of humidity, different temperature at 80, 100 degrees. The Nafion has quite constant values of the permanence as this relative humidity is increasing. At under 20, dramatic dropping down. That's one of the limits that we know, and you can have some other effect in the other case. Either permanence value was obtained at 75 relative humidity, and the membrane is going to stop really working, etc. You can hear some this lower permeability than Nafion in all the operating conditions, and that is a positive result, as I was mentioning before, basically. Basically, in all conditions, this kind of polymer has a better performance than Nafion for what concerns this Nafion permeability. One more characterization that is quite interesting, in all the experiments you are doing, you are measuring, we want to know the ion conductivity of our membranes. And that is a typical easy experiment you can do using direct current, and you put your membranes, you apply your voltage, you just measure, you apply Ohm's law, and you have the resistance of the system, and if you have the resistance, you know how there is a change, you know also the conductivity. That is just what normally people have been doing. Today, some of you is also expert, you can change, you can do a little bit better than this, and that is necessary because we have been learning that in this system, this ion conductivity can be apparently different, not because the membrane is different, but because other problems take place in the system, and this problem, exactly as the one we were talking before in terms of going up and down with relative humidity, etc., can affect the final performance. So instead of working with traditional direct current, applying the Ohm's law, you can work with impedance spectroscopy. That means you are not working with direct current, but you're working with alternating current. If you're working with alternating current, you have a different, you can have a totally different behavior. You have to talk about impedance instead of resistance, and there is a little bit more complicated performance, and some of you, I mentioned, is expert. But the main reason for doing this is more than this. Is just the fact that let's see. We'll go back later, but I want to show one thing if we arrive quickly. We don't arrive quickly, so don't worry. This method is interesting because basically you can follow not just the proton conductivity of the system, but you can follow the changing with time of the overall conductivity of your system. Because what is happening with the impedance spectroscopy is that you can easily differentiate between the ohmic resistance and the resistance related to the double layer or to diffusion layer you create in the system with time. So if you want, for example, to study fouling phenomena that are taking place in the system, no way to make any fouling study with direct current. This is the way, I don't have here the slides I was trying to show you. You can follow with time and you see how this system is changing in protoconductivity, in overall conductivity related of the growing of the double AID interface. Quite interesting, very difficult, and that is one of the major problems that has to be solved today. We learned that to understand not just the intrinsic property of the membrane, but how the membrane behaves when it's working and what is happening in the system. For example, during this kind of making this kind of experiments, you can realize easily then that some of these ions that are present in the solution can just kill your system. Magnesium, for example, in some kind of membranes when you are working in PRO or on the reverse electrodialysis, we will see when, that's why. Now I remember where are the slides. When we'll discuss about the reverse electrodialysis, you will see the slide I was talking now. You will see how the system is changing, and just because this fouling is growing, and some ions, magnesium for example, can just block the membranes, much more than sodium chloride or other. So if you have a solution in which magnesium is present, you have to be careful because the membrane stops working for the magnesium, not for other reason, which is also giving you an answer. You can remove magnesium and the system will work. But there is no way to understand this if you are not using methodology of this kind. In this case, we will discuss this talking about the reverse electrodialysis and where we have this slide showing this. Basically here to show this, the results, if you are doing this, you can measure this proton conductivity is a different temperature, and you can see how that is changing with relative humidity, and the comparison between our peak and this Nafion is always of this kind. Nafion is always much higher proton conductivity, but increasing in temperature, when you arrive 120, you can see here that with peak, still no evidence of any degradation, and with Nafion, you're dramatically going down. As that is one of the point of suggesting that it makes sense to spend some more time for doing these kind of things. The performance of these membranes can be measured at different temperature as a function of the relative humidity, and this behavior is still confirming what was mentioned before. Here the same story with this is the transport numbers, but anyway. What you have here is all this case, the ion exchange capacity. You can see here that Nafion is always a much higher ion exchange capacity than all the other one. And also when we are adding our acid, not enough to compete with Nafion up here. And this is one of these good aspects of this Nafion. What is interesting is that also here for the HPAS, that means for any kind of acid we are adding, and this again, this Nafion is, oh no, wait, this is just showing you how the system changes. When there's no acid, we can change significantly the overall, depending from the ion exchange capacity, from the single polymer to the one added with the superacid, and that is this, the ESC is higher for the composite membrane than for the polymer one, as expected, otherwise there was no reason for doing this, but the same amount of HPS has a significant influence on the product conductivity, and that is just what is shown here. So just this is just to show you that this effect of this additive, in principle, can change significantly the overall performance of your membrane. However, for what has been done until now, you don't know. It's interesting results, interesting publication, but Nafion is still there. So we are not still able, and if you increase more than 20–30% the presence of our superacid, you start to lose mechanical properties or you have leakage. So you have to find something different or a different way, a different kind of superacid or a different way to immobilize in the membranes. So that is basically. And this is just the same data showing. And remember that at the end of this story, that's what is summarized here, that when we are talking about this fuel cell, this is not just the fuel cell itself, because we have always to produce hydrogen and to have this system working in an overall system where, for example, the temperature we are discussing is also a very critical parameter. Working at 80 or 120 is not just a question of temperature, it's a question of the system in which you are working that sometimes will permit you or not permit you to change the temperature in the range that you like. That's why that is because we are always part of our overall system. And that's why also these exergetic analysis that they are taking care of these different temperatures that are in the system has to be considered. To conclude this part, just to show you that this is the first example of membranes utilized in energy production, basically. Fuel cell is number one. We learned that that's nothing more than a traditional battery, open. A battery that is not a closed system, but is an open system. Basic equations are the same, but we've been learning also in other things, that for doing this, the system is much more complicated than expected, because it's not only a membrane. It's a membrane with all the transport phenomena at the interface in the solution and all the engineering for optimizing the behavior of the membrane, minimizing activation energy, over potential, concentration, polarization, etc. And that's giving you a lot of instruction on the control of the temperature, on the control of the humidity, and so on. Bottom line is that one polymer is still dominant, Naphthalene, but people are trying to find something better, otherwise it would be difficult to have big success of this discussion, and the field is open. There are new polymers people are working. That's the case. We have been working this polyether ketone with Cardo group, but you are working with some other one, polybenzimidazole is typical case, and others. However, you must be careful in really understanding not just proton conductivity, because that is not enough. You have to see all the other parameters, and you have to make comparison, being careful how you make your comparison, because sometimes the procedure are much more complicated, and I show you one slide, you have to take care. There's a lot of mass transfer in the system, 7 flue gases, hydrogen gas are there, and if you want to describe the efficiency, that means to compare your result with the other guy, you must be sure what you are measuring and how you are measuring. If not, there's a lot of confusion in the literature and no result at the end, basically. Okay? Question, information? We will meet. You receive already all the material for fuel cell? Not yet?
Yes. Yeah, I didn't distribute them because there's some problem in distributing, so I'm going to distribute it.
Let me know so we can make it in a different way. I can send directly from home just to the address. If there is any problem, you mean a problem with the scanning here?
Because I forgot to distribute the material. So
anyway, we talk later. If nothing arrives, and in the couple of days from now, just when we meet on Friday, let me know and we will try to solve the problem in a different way. Okay? Thank you.